Good afternoon, everyone. Today we are going to do the lecture for Chapter 1, Section 4 over complex numbers. But before I start with the notes that are on the board, I wanted to show you this graph, this diagram of what complex numbers kind of are. Complex numbers are kind of this unique area of numbers that we don't spend a lot of time on. And so they don't get a lot of attention. And so you might not even recognize what they are, or you might not realize how they're different from other numbers or how they're the same. And so this little diagram that I pulled up on the computer is actually really nice because it shows you all the different styles of numbers that we kind of generally talk about, such as the natural or counting numbers, which are there in the most inner circle of the biggest circles. Those are, it says counting numbers. So when you start counting, you start 1, 2, 3, 4. Right outside of that are the whole numbers, which are the counting numbers plus the number 0. Outside of that is the integers, which are the positive and the whole numbers. So it's all the whole numbers plus all the negatives. Then we get into rational numbers, which can be written as a fraction or a repeating decimal or a terminating decimal. Then we have the irrationals, and those are the weird ones like e and pi and the square root of 2. And all of those are classified under these real numbers. These are real numbers. Now, if you look though, there's this big blue box around the real numbers that says the complex numbers. And then there's this little circle out here to the side that says imaginary and pure imaginary numbers. So that's kind of what we're going to delve into today. Complex numbers, if you notice though, it includes the real numbers and it includes the imaginary numbers. But today we're going to talk mostly about complex numbers that have some imaginary unit with them, at least for part of the time. So I just wanted you to see that complex numbers, they can be imaginary, they can be real, they can be both. That's totally okay. So I will stop screen sharing that just because it doesn't really add a lot to our lecture from here on out, but I wanted you to see how the numbers kind of fall in with that. So there's the start of our notes. So section 1.4, complex numbers. So before we start talking about complex numbers, as you saw, the complex numbers was the broad blue scope, and that included real numbers and imaginary numbers. So let's talk about the imaginary unit. The imaginary unit is usually signified with a lowercase I, and the lowercase I, or the imaginary unit, is equal to the square root of -1. If you remember, when we take square roots, we can't take square roots of negatives because the square root of a negative gives us a negative number and a positive number. Well, that's not a perfect square, so we've never been able to deal with that. Well, now we can do that because we can talk about it in terms of the imaginary unit, this I. So I is equal to the square root of -1. And because that is true, then I squared is equal to -1. This will allow us to play around with expressions that have the square root of negative numbers in them. And that's exactly what we're going to do with our first example, which I'm going to rewrite because I noticed my negative kind of just got shoved in there haphazardly. Okay, so we're looking at the square root of -25. Well, when we talk about this in terms of real numbers, we can't do that. We can't have the square root of a -25. However, if we're also including the imaginary unit, then we can. Because what this says is we have the square root of -1 times the square root of 25. Well, that's okay. We can do the square root of 25. That's just 5. And we just discovered that the square root of -1 is I. That means we have 5I. Because this went to an I and that went to a 5, so we have 5I. So the square root of -25 can be written in terms of 5I. Okay? So let's talk a little bit about complex numbers. This is the definition of what complex numbers are. I'll stand on this side so that if you're still writing over there, you can still see it. So the complex numbers is the set of all numbers in the form of A plus BI, with A and B real numbers and I the imaginary unit. So that was the big blue box that went around the imaginary numbers and the real numbers. That's the complex. They can be written in the form of a plus bi. So here are some examples of complex numbers. We have -4 plus 6i, a plus bi. 2i is also a complex number because you could write that as 0 plus 2i, a plus bi. Even the number 3 is considered a complex number because we can write that as 3 plus 0i. That's why all real numbers can fall into the complex number category, is because we could write it in terms of 3 plus 0i, or whatever plus 0i. So those are complex numbers. So complex, again, was the big blue box. Let's get this table a little closer. Okay, so complex numbers, you can have a 0 as your B. Imaginary numbers, that was the little circle over to the side of the, like there was a real circle and then there's the imaginary circle. And those are all under the complex box, but the imaginary circle is a plus bi, where b does not equal 0. So 3 is not imaginary. 3 is a real number, and that's because we have 0 for I. Now 2i isn't real, it's imaginary, because you can write that as a plus bi. So a can be 0 in the imaginary numbers, but b cannot be 0. So here's an equality. This is kind of a logical thing, but I wanted to make sure and write it out so that you had it in your notes as well. So it's the equality of complex numbers. That says that two complex numbers, a plus bi, equals c plus di if and only if a equals c and b equals d. So only if these separate components equal does the whole thing equal. That's kind of well, duh, but it's nice to mention so that when you compare them, you know when they're equal and when they're not equal. Okay. Remember, if at any point during any of my lectures I'm going too fast, the nice thing is that they're recorded. So you have the option to push pause and keep recording things, or also pull up my digital notes and copy from there, because I'm going straight off of my notes. So how do we add and subtract complex numbers? Well, here's the long steps, but in essence, all we're doing is combining the like terms. We combine the real parts. So if we have two complex numbers, a plus bi plus c plus di, then we're going to add the a plus the c, and we add the b plus the d. So we add these first parts, the real parts, then we add the imaginary parts. Same thing is true for subtraction. You subtract the a and the c, and then we subtract the b and the d. That's all we do, combine like terms. So here's our first example. 5 minus 11i plus 7 plus 4i. So I'm going to regroup this so that I have my real parts together and my imaginary parts together. So I have 5 plus 7 minus 11i plus 4i. So now I add these parts. So I get 12, and negative 11i plus 4i is minus 7i. I took out the real parts, and then I added or subtracted the imaginary parts, whichever way you like to look at that. And that's all I did. Do one more example of this. That is not going to balance. Sorry, you're going to have to be a little further away. So I'll try to make it a little bigger for this one. We have negative 5 plus I minus a negative 11 minus 6i. The reason why I wanted to do an example like this is because I wanted to make sure to reiterate that when you have a minus and a minus together, it's going to become a positive number. So don't drop those negatives there in the middle, okay? So we have negative 5 plus I. Now I'm going to distribute this negative in to each thing in my second parenthesis, and that's going to make them both positives. Negative times a negative 11 becomes a positive 11. Negative times a negative 6i becomes a positive 6i. So I now have minus 5 plus 11 plus I plus 6i. Minus 5 plus 11 is 6. I plus 6i is 7i. Bring it a little closer so you can see, just because I know I had to do it from back far away. So I distributed that negative in. I made both of those things positive so that it turned a subtraction problem into an addition problem. I added my real parts, I added my imaginary parts, and I got 6 plus 7i. Notice when we write complex numbers, we usually write the real part first and then the imaginary part second. Okay? So that's adding and subtracting. So what do we do then if we want to multiply? Well, for multiplying complex numbers, then there's two things we can do. We can either distribute or we can use the FOIL method. Remember, FOIL stands for first, outer, inner, last. It's like the reverse of factoring. Okay? So let's look at this first example. We have 4i times 3 minus 5i. So in this case, we have one thing outside the parentheses and two things inside. So when you have that, you're going to distribute. That means you take 4i times each thing that's inside. So we have 3 times 4i minus 5i times 4i. 3 times 4i is 12i. Minus 5i times 4i would be a minus 20i squared. Now, if these were just x's, that would be where we'd stop. However, since these are imaginary numbers and that I is actually the imaginary unit, then we need to think about something. I squared is what? What did I say all the way back at the beginning? I said I squared is the same thing as negative 1. That's like saying we have 12i minus 20 times negative 1. That means we have 20 plus 12i. That negative times the negative is going to make that a positive 20. So I put my real part first, 20 plus 12i. So that's something to remember. Anytime you're simplifying these things out and you get an I squared, you're going to need to substitute in that negative 1. And be careful, because that negative 1, it didn't add to the 20. We didn't have a negative 21. They were multiplying here. So when you put them in, you're still multiplying them. Okay. Do another one. 7 minus 3i times 2 minus 5i. So in this case, we have two different parentheses, and each parenthesis has two separate items inside. That's when we're going to use the FOIL method. Just like if it was x plus 2 times x plus 3, we're going to use the exact same method. So FOIL means first, outer, inner, last. So I do my first, 7 times negative 2, which is negative 14. I do my outer, which is 7 times negative 5i, which is minus 35i. I do my inner, negative 3i times negative 2, which would be a plus 6i. And then I do my last, negative 3i times a negative 5i will be a 15i squared. So I have negative 14, 35i, negative 35i plus 6i will be a minus 29i plus, and then I have 15i squared. And just like on the last problem, I squared is the same thing as negative 1. So negative 14 minus 29i minus 15, because 15 times negative 1 is negative 15. So I have negative 29 minus 29i. Okay. So the trickiest part is making sure to substitute in that I squared is -1. So that's multiplying. So how do we do division? Well, before we can do division with complex numbers, we have to learn a new concept. And the new concept is called complex conjugates. So we use the conjugate of complex numbers in order to get real numbers, like to get rid of the imaginary part of our numbers, and to divide by complex numbers. So if we have a plus bi, then the conjugate is a minus bi. Notice we didn't change the a, we didn't change the b. All we did was we changed the sign in between them. Similarly, a minus bi, the conjugate will be a plus bi. The reason for this, and we kind of talk about conjugates maybe without using the word conjugate whenever we talk about factoring and foiling and coming up with perfect squares, because that's really what we're doing here. We're coming up with a perfect square for our complex numbers. So if we have a plus bi times a minus bi, then we're just left with a squared plus b squared. If we do FOIL, we do a first, outer, inner, last. That middle term that we usually get goes away when you're multiplying by the conjugate. And that's why we do it, because it's that middle term. Let me angle back over here to our problem. It was this middle term right here that had the I in it, that -29i. That's where our imaginary number was in that middle, the outer and the inner. When we add them together, we get that middle term, which is our imaginary number. So in order to get rid of that, we have to have a perfect square. And to have a perfect square, we take the complex number, we multiply it by its conjugate, and that gives us the perfect square of a squared plus b squared. And since it's multiplication, it doesn't matter if we have the a plus bi first or the a plus bi second, it's going to work either way. So I will do an example, because sometimes words are more complicated than just seeing the problem worked out. So here's an example. We have 3i, and then we have we have 3i over 4 plus I. So this is our problem. We want to do this division problem. So how do we simplify this? Well, to simplify this, first thing we have to do is we have to find the conjugate, and then we have to multiply the top and the bottom by the conjugate. Okay, so what is the problem? The problem is that we have an imaginary unit on the bottom part of our denominator. We don't want that. We want to get rid of that. We only want whole numbers or real numbers in here. So to do that, we need to come up with the conjugate. We have 4 minus I, or 4 plus I. So the conjugate then, we don't do anything with the 4 or the I, we just change the sign. So my conjugate then is 4 minus I and 4 minus I. Whatever we do on bottom, we have to do on top. Now we'll use our multiplication where we distribute on top and where we FOIL on bottom. That FOILing method, though, is going to eliminate that middle term. And I'll write it out all the way so that you can see it, okay? So let's look at the top first. We have 3i times 4, which is 12i, and then 3i times a negative I, so minus 3i squared, all over. So we do our first, which is 16, 4 times 4. We do our last, or our outer, which is 4 times negative I. Do our inner, which is 4 times positive I. And then we do our last, which is a minus I squared. So notice here, our middle term, we have a minus 4i and a plus 4i. So those are going to go away. And that's why we multiply by the conjugate. We want that middle part to go away. Now, the other thing we need to look is we have a couple of I squareds. So we need to remember that those are negative 1s. So we have 12i plus 3 on top. And we have 16 minus a negative 1. So that's going to become a plus 1. So I'm going to flip-flop these so that we have 3 plus 12i all over 17. Now you can leave it like this. That is totally fine. Or you can separate it out so you have your real part plus your imaginary part. Either one of these is correct. I typically will take it out this way just because I like it to look like A plus BI, and this is A plus BI. So if you find the conjugate, you multiply top and bottom by the conjugate, you simplify it out. You still get a complex number, but it got rid of the imaginary unit on the bottom. We'll do another one. That's good. So here we have 7 plus 4i over 2 minus 5i. Again, you have to come up with the conjugate. Conjugate is just whatever's on bottom, you change the sign. So we're going to multiply the top and the bottom by 2 plus 5i over 2 plus 5i. Now, the first one, our top was just the 3i, and so we got to distribute. Now we're going to have to FOIL both the top and the bottom. Okay, so let's look at the top first. I have 7 times 2, which is 14, plus 7 times 5i, which is 35i, 4i plus 2 is 8i, 4i times 5i is 20i squared all over. And then here, I'm just going to get 4 minus 25i squared. So start combining my like terms. I have 14 plus 35 plus 8 is 43i. That I squared becomes a negative 1. So that's a minus 20 all over. I have 4, and then the I squared becomes a negative plus 25. 14 minus 20 equals a negative 6 plus 43i all over, and the 4 plus 25 is 29. Again, you can leave it like this, or you can separate it out to where it would be negative 6 over 29 plus 43 over 29i. Either of these is correct and acceptable. So working with complex numbers, you will get pretty good at doing your FOIL method, which is good. It doesn't really go away, so it's good to know. Okay. Now we're going to talk about something about the roots of negative numbers. So when we talk about squares, like the number 16, well, the square root of 16 is plus or minus 4. And we say it's plus or minus 4 because if you have minus 4 times minus 4, you get 16. If you have positive 4 times positive 4, you get 16. So both positive 4 and negative 4 are called roots of 16. So now that we have imaginary numbers, we can talk about the roots of negative numbers. Okay, it's the same process as with real numbers. It's just now we can do it with negatives. So we're going to start by looking at it kind of backwards. So we have 4i quantity squared. Okay, that's 16i squared. Remember, I squared is negative, so that's negative 16. Or we have negative 4i squared, which is 16i squared, which is negative 16. Again, similar process to what we just did right here. And so what we say then, or what this tells us, is negative 16 has 2 square roots. And we say that 4i, the positive one, is the principal square root. just like with our real numbers, we had a positive and a negative. You have a positive and a negative here. But we call the positive the principal square root. It's why it's pretty similar to in the real numbers, where when you think about the square root of 16, 9 times out of 10, you're really only going to think, well, it's 4. That's true, but it's not totally true because negative 4 is also a square root of 16. And so we're saying this to make it nice. We're going to use the principal square root theorem here in just a minute, and that helps us to simplify our radicals. So you can already, I notice it's already on the board, so I'll go ahead and talk about it. The principal square root is simply that the square root of negative b is I times the square root of b. And so we can say the square root of negative 16 is the same thing as I times the square root of 16. We can just pull out that I, and we're able to do that because square root of negative 16 equals the square root of negative 1 times square root of 16, and that's I times the square roots of 16. That's the very first example we did with the negative 25. We can just pull out that I and then just deal with the square root that's under the radical. Okay, let's go do a couple of examples. We're almost done. All right, first example. We have negative 25, or square root of negative 25, times the square root of negative 4. So based on this principal square root that we just talked about, we can pull out those negatives as i's and then just deal with the radical underneath. So square root of negative 25 is the same thing as I square roots of 25 times I square root of 4. Well, what is the square root of 25? It's 5. So that's 5i times, what's the square root of 4? 2. So that's 2i. 5 times 2 is 10. I times I is I squared. I squared is a negative, so that becomes a negative 10. That's why it's real important that up here at the very first step, we don't just say, well, negative 25 times negative 4 is a positive 100, and the square root of 100 is 10, because that's not what we're getting. We're getting negative 10. We have to pull out those i's first and then simplify it down. Okay, our second example, we have negative 8, or square root of negative 18 minus the square root of negative 8. So again, let's pull out those i's. So we have I square root of 18 minus I square root of 8. Okay, now we have to kind of think about, these aren't perfect squares. Over here we have 25 and 4. Those are perfect squares. We got rid of our radicals. They went away, all nice and neat. But that's not what's going to happen here. So is there anything that that's squared that is a factor of 18? Well, you have to think about what are factors of 18. What times what gives me 18? 1 and 18, 2 times 9, 3 times 6. Well, 9 is a perfect square, right? So let's take 9 times 2 minus I, and the same thing here for 8. Is there anything that we can multiply together to get 8 that's a perfect square, or has a perfect square as a factor? Yes, 4 is a perfect square, and you multiply that by 2, and you get 8, right? So now what we're able to do is we can pull out these perfect squares. So the square root of 9 is 3, so I have 3i square root of 2 minus the square root of 4 is 2, so I have 2i square root of 2. Now, I don't know if you're really comfortable with your radicals or not. You're going to have to get more comfortable with them in complex, when we're dealing with complex numbers. It's adding and subtracting radicals is very similar to adding and subtracting fractions. When you add or subtract a fraction, you have to have that common denominator. When you add or subtract radicals, you have to have the same thing under the radical. or you can't add and subtract them. So we have square root of 2 here and square root of 2 here, so that means we can subtract them. That means we get I square root of 2. If they were not the same under there, then we would not have been able to take it any further. But they were the same, so we were good to go. Example C. We have -1 plus the square root of -5 quantity squared. Okay, so let's write that as -1 plus the square root of -5, -1 plus the square root of -5, like that. That way, we're going to know we're going to FOIL here in a minute. But before we FOIL, we need to pull out that I. Okay? -1 plus I square roots of 5 times -1 plus I square roots of 5. Now we're able to do our FOIL method. -1 times -1 is a positive 1. -1 times I square roots of 5 will become a -I square root of 5. Again, -I square root of 5. Then we get plus I squared, and then square root of 5 and square root of 5 becomes a 5. I'm going to write that before the I squared. 1 minus 2I square roots of 5. And then that's a -1, so that's a -5 minus 5. So we get -4 minus 2I square roots of 5. So the trick here is when you're squaring or you're FOILing and there's a negative under the radical, you want to pull that I out first before you do your FOILing or your multiplying. Okay. One more example and then we are done. Last example. We have -25 plus the square root of -50 all over 15. So we have -25 plus, I'm going to pull out that I, there's no minus anymore because I pulled it out. Square roots of 50 all over 15. Again, 50 is not a perfect square, so we have to think about what times what gives me 50 that may have a perfect square. Well, 25 times 2 gives me 50, right? 2 quarters makes a half dollar, and a quarter, or 25, is a perfect square. So I have -25 plus I, square root of 25 times 2 all over 15. So I have -25 plus that 25, square root that becomes 5. 5I square roots 2 all over 15. So I can't combine anything else because I have a radical. I don't have anything else, but I have a -25, I have a 5, and I have a 15. Do those have anything in common? They do, they have a 5. So we can reduce those down and make them simplified, okay? So we can take a 5 out of everything, which will be a -5 plus I square roots 2 all over 3. And then you can leave it like this, or you can write it as -5 over 3 plus 1/3 I square roots 2, like that. Either way is correct. But that's one thing we haven't had any where we really needed to reduce. And so you need to look for those common things that maybe you can pull out after you've done everything else. You don't want to pull things out until you've done all the other math. But at the end, if it still needs to be reduced down further, you can pull out the common factor. So that is it for Chapter 1, Section 4, Complex Numbers. Hope you have a good day.